Hello everyone. In this lesson, we're going to talk about limits. And that is one of the most important ideas in calculus. Almost everything in calculus, derivatives, integrals, they're built upon the idea of limits. So it's very important for us to get a good and very intuitive understanding of what a limit actually is. So in this video, we're going to start with a very simple example and use it to understand the basic idea behind limits. Let's get started. All right, let's take a look at this function. F of x is x cubed minus 1 divided by x minus 1. So a typical rational function. So if we want to sketch the graph of this function, what can we do? Well, of course, many of you will say, can we just keep generating values of x, right, and put them into the function and just go ahead and make a lot of points, right, on a graphing paper, and then go through the points with a smooth graph, right, or as smooth as you can make. You're absolutely right. But there is a very interesting point, a point that's going to cause some problem, and that is x equal to 1. Right? What's going on when x equal to 1? Well, as you can see that you're going to get a 0 denominator, right? So any division by 0 is undefined. So now here's a very interesting question. So what if we insist that we want to know the behavior of the function f of x when x is exactly equal to 1? Well, but technically speaking, the function of f of x does not even exist, right? Because it's not even defined at that point, since we just cannot have a 0 denominator, right? Well, hold on. I mean, even if we cannot really take x to be 1, otherwise, the function will be undefined, right? But nothing's going to stop us to play around with values of x which are super close to 1, right? As long as x is not exactly 1, we're protected. Right, so we can do that just by, keep generating some values of x, right? Make them to be close enough to the 1, right? Let's see what happens. All right, so let me make a table. All right, so you can see that we are taking the value of x. We can start with 1, but you know that when you put in a 1 for x, the function f of x can complain, right? So we don't know what's going on at this particular point. But we do notice, as we're taking the value of x closer to 1 from either side, right? Let's say, start from 0.75, then go to 0.9, 0.99, 0.999, right? Or it can also go to the other side, right? So let's say start from something a little bit bigger than 1, right? Starting from 1.25 all the way, to however close you want it to be 1, but it's always going to be a little bit greater, right? So as you can see that it's quite interesting that the function value, right, are getting closer and closer to a number. Well, of course, we couldn't see exactly what that number is, right? But I think that we can tell based on trend, right, of the function values on, this chart. So we believe that f of x is definitely approaching the value of 3 when the x is getting closer and closer to 1. Okay. Now, let's see if we actually graph this function, if the graph's going to make sense, or at least that if the graph's telling us something that's consistent with what we found from the chart. All right, so let me show you the graph, right, of the function. All right, so as you can see that we're looking at a pretty nice smooth curve and looks like a parabola. But just so you know that not every curve that looks like a parabola is actually a parabola. Right? But in this case, you're not wrong if you realize that the shape looks just like a parabola, and we can show in a few minutes. Okay, but before we do that, right, let's take a look at what the graph's trying to tell us. What is a hole here? A hole is like a missing point, right? That's why you have like an open circle, right? So that point is missing. But what is that point? So that point is located at exactly the point that we were very interested in, right? So you see that x equal to 1 is a bad point, right? So you cannot really take x to be 1, and that's why the graph says that, no, we don't have a point like that, so that point is missing. But when x is approaching 1, right, we can start from, the data chart, the function is going to be approaching to the number 3, right? And therefore, if there were a point on this graph, it would have been a point located at x to the 1, y equal to 3. But that's a missing point, right? But now the question is, how do we know that the function is approaching the 3? Well, you might say, Dr. Wang, are you kidding me? Isn't that obvious? As you go follow the trend of the graph, right? So let's say as you're going from somewhere to the left of the point x to the 1, right? So we follow the trend of the graph, right? You can see that the curve is approaching to that vertical value of 3, right? You can see that from the other side of the graph, right? Just follow the trend of the graph. So there's no way we can miss that trend of the graph, right? So it's just pointing at that number 3, okay? And that says something about the concept of limit. All right, so now in calculus, we want to write down this idea using the limit notation, okay? All right, so by limit notation, I mean we're trying to specify when x approaching to a specific number, and the function f of x will be approaching to a number that tell us, quote unquote, the limit of the function. In this notation, LM, which, as you know, that's going to be the brief, abbreviation of the word limit, right? You put something underneath the letters LRM, right? So X with an arrow telling you that this is the ultimate direction that you want the X to put to approach, right? So X is approaching 1, but X is never going to be exactly equal to 1, right? So please notice that there's a big difference between you draw a arrow between an x and a 1, right? So you're saying that x is approaching a 1, and you claim that x is equal to 1, right? They are two different things, okay? Now, what does it mean? The limit of x, the limit of f of x as x approaches 1 is 3. This is just telling us that, hey, just like what we did, right? So we're looking at a certain value of x and we want to know what's going on, but somehow we realized that we couldn't really evaluate the function exactly at x equal to 1. So what we do is we take numbers of x to be super close to 1, and let's just try to find the trend of the graph, right, or the function. See that when the x is approaching to the number, let's say 1 from the left, right? Let the x to be smaller than 1. Let's see what approximately the f of x is going to be, and we can try the other end, right? So let the x to be greater than 1, right? Let the x getting closer and closer to 1, but still be greater than 1, and let's see what the function f is going to be, right? But with that much, information we can get from the graph, the data chart, we realize that it would have been a lot easier for us to just put all that much information into one single statement, right? Because we already realized that there's a very interesting behavior of the function f of x, which says that if the x is super close to 1 and the function value is going to be super close to 3, right? And it works out whether or not x is greater than 1 or less than 1, right? And we don't care about whether x is going to be equal to 1 or not, right? Because all we care is the trend of the graph, right? The trend of the function f of x, and the trend is 3, okay? Now, let's take a look at another example. All right, so now we have a function that involves, again, fractions. That means, potentially there will be some problem with the denominator, right? Like you saw in the previous example. And also we have some radical expression going on, right? Hopefully it's not going to freak you out that much. So let's see. We're trying to figure it out when x is near 0. Or let's say, it's just getting super close to 0. What will be the trend of the function value of f of x? So we're trying to do the same thing like we just did, right? But I mean, the fancy way to say that is to get the limit of the function f of x when x is approaching 0. You put the limit notation like that. Now, of course, a very common way to do that is, like you saw previously, we draw a data chart, right? Trying the numbers to make the x to be x close to the number, let's say 0, right, as we could, and see what happened to the function value, right? Or you can just graph, right? Well, not to say that you have to graph on your own, because nowadays, we can take advantage of, those graphing technology, right? The online graphing calculator, or the one you have, probably the TI 8384, right? Yeah, use them. So here I'm going to show you a screenshot of people using TI 83, I guess, to investigate, right, what's going on with the function value when x getting closer to 0. So as you see from this kind of funky interface, right, but it's good enough for us to know what's really happening. So of course, when x equals to 0, it's problematic, right? As you can see that here, you take x to be 0, the denominator could be evaluated as radical 0 plus 1 minus 1, right? This is really 1 minus 1, so it's 0, right? And again, you have a 0 denominator, and that's why the calculator complains, right? You have an error there. But as long as you can avoid taking x to be exactly 0, so you can try, say, plus or minus negative, plus or minus 0.001, right? Or, even getting farther away. But you know that the essential idea of the limits is that you want to take the x to be as close to the number you want, right? So work your way from farther to the nearer, regime, to see that when the x getting closer, right, to the value you want, and what happens to the function value. And I hope you can see that. The trend of the function seems to be 2, right? And we can also confirm that with the graph. So we actually plot the graph, right? Well, of course, we asked the calculator to do that for us. And not surprisingly, as we can see that there's a missing point there, right? Located at x to the 0, right? Because you're not supposed to take to be x to be exactly 0, right? The function is undefined. You have a 0 denominator. But what's interesting is where that missing point is located. You can see from the scale, right? The vertical scale is like at 1, 2, it's like a 2 increment, right? Going up there. So this is telling you that the y value or the function value is going to be 2. Okay. Well, does it make sense? Yes, of course, right? Because we already see from the data chart, when x approaching 0, the function either from one side or the other, right? However, the x approaching the 0, the function is pointing at that number 2. And the graph confirms that, since as you follow the trend of the graph, right? Let's say that the x is getting closer to the 0 from the left, right? The function is rising and getting closer and closer to that vertical value of 2, right? And it works out the same way as you go from the other side of the 0, right? X is getting closer and closer, but still being greater than 0, and the function value is going to go down, and eventually it's going to pretty much hit that same point where the y value is going to be 2. Okay. So I think that with these 2 examples, especially the first one that introduced us, the idea of a x approaching to a number, and we can investigate, what's going on with the function f of x. We know that the function is not even defined at the point we're studying. Now, with the second example, it just confirms, right, what we have done to the first example. So we gain the confidence that even though that we probably couldn't really do a limit problem right away, right? Like, purely through some algebra, but you should have the confidence that with the graphing utility, with the techniques of simply just plug in numbers of x, right, and make the x to be as close to the number you want to see what's going on with the function value. So that's almost always going to work out. Okay. Now, before we finish, there's one really important thing to point out. So in both examples, as you may recall, the function isn't really defined, right, at the value that we want the x to approach to. Okay. Or let's say, just take a look at the second example here, right? So the function f of x is not defined at the number of x that we want it to approach to. Okay, so that's super important. That says a lot of things about the concept of limit. Okay. So let me ask you to seriously think about what I'm gonna put on the screen in a second. And that will be the most important takeaway from this lesson. Okay. All right, so I'll read it aloud to you. So the existence or non-existence of f of x at x equal to c, where c is just going to be, a actual number like x equal to 0, right? In the second example, x equal to 1 in the first example. So the existence or non-existence of f of x at x to the c has no bearing on the existence of the limit of f of x as x approaches the c. Well, what does it mean? I'll let you process for 1 or 2 seconds. Now, don't you see that this conclusion is trying to address the confusion between the existence of a function at a certain value of x and the existence of the limit of function f of x as x approaching that number you want. So let's say the limit as x approaches c of f of x versus f of c. You guys know the difference, right? So the things on the right is the function value. It's how much the function f is defined to be when you take the x to be exactly equal to c. Well, the things on the left, right? We've been spending the past 10, 15 minutes, right? Discussing, hey, what if I couldn't really get to exactly the c? So x is going to be super close to c, right? But could be always less than c, right? Or greater than c. But when x is approaching c from either direction, how much should be the value of the function if we were to be able to take this x to be exactly c, right? How much will be f of x? So what is the trend of the function f of x? Okay. And the things on the left, well, as you can even tell from the limit notation, right? This is the limit of the function f of x. Where the things on the left, on the right, sorry, is the definition of f of x. Right. So these are two very different things. Okay. So they might be almost always closely related to each other, right? But they are very different. Right. So now logically, let me give you analogy so you can find the correlation, but also more importantly, the difference between the limit of a function and the definition of a function. Okay. So let's think about two things in our life that we're so used to. First off is if it rains out there, right? And then the second thing is you're gonna use umbrella. Okay, so these are the two things, and I think that almost everyone agreed that these two things usually come together, right? And you're thinking there's some causal relation, right, between raining, right, and using umbrella. So do you realize that there are often times when it does rain, but you don't use umbrella? Or there are often many times and it doesn't rain, and you're using the umbrella. So what do you think this is telling us? Is the raining condition the cause of using umbrella, or vice versa? I don't think so, right? Well, they're related, of course, right? Because most likely, if it rains, you're going to use umbrella, right? Or whenever you see people using umbrella on the street, that most likely it rains, right? But we're not using umbrella doesn't say anything about whether it rains, because there are exceptions, right? People use umbrella maybe to block the sunshine, right? Um, and also, whether or not it rains has nothing to do with people using umbrella, because let's say I'm in the United States, it shocked me in the first couple of years I'm here, because I realized that I'm probably the only one on the street that's using umbrella when it rains. And I feel like that people here, they probably don't even know what umbrellas are. Well, I'm joking, I think that they know, but they just almost never use them, right? Um, so, and that's the idea I want to give it to you about whether or not you're able to find the function value or the definition of a function f of x, and whether or not you'll be able to find the limit of the function f of x when x approaching to a number you want. So these are two different things, okay? And this is where most of our students are going to get confused, especially in AP exams. There will be easily multiple choices testing you guys to see if you can be even confused by the definition of the function, and you might mistaken it as the limit of the function and vice versa. Okay. Anyway, so I think that's good enough for this lesson, right? Just trying to introduce you the basic idea about limits. So hopefully, this helped you understand the limits a little bit more clearer. Feel free to subscribe more AP Calculus lessons. Now, and if you're studying AP Calculus and need some extra help, I also offer one-on-one tutoring, and you can find more information in the description down below. Thanks for watching, and I'll see you in the next lesson.